In this lecture, we'll talk about how we can encode things in a computer using bits, and we'll also talk about how many bits do we need to encode a particular number of unique things. So everything in the computer is in binary. And what's binary? Binary is base 2. Why do we care about that? Because we can use ones and zeros to represent anything in a computer. We can represent numbers, we can represent characters, we can represent pictures, we can represent sound, we can represent anything with zeros and ones. That raises the question though, first, how do we do it? And second, how many bits do we need to represent a particular number of things? And that requires me to tell you a Christmas story. So my family, several years ago, were trying to figure out who gets to open the first present. That's part of our tradition of Christmas. And we wanted to do it with coin flips. So we were thinking about how many coin flips did we have to do to pick out of 4 people. One of my children was not there yet. Out of 4 people, how many coin flips did we have to do to figure out who opened the first present? Now, me and my son, a computer scientist, came up with one answer, and my wife and daughter came up with a different answer. So you should pause the video for a minute and think about how many coin flips you would need to do to actually pick from 4 people the person who gets to open the first present. Once you've figured that out, go ahead and unpause the video and I'll talk through the 2 different solutions that we came up with that Christmas morning. Okay, one of the common solutions that we might use would be to have a tournament. This is sort of a standard structure that you see in, playoffs in hockey or some other inferior sport to hockey. So you have these ladders, if you will, and you have A plays B and somebody wins, and that would be 1 coin flip. C plays D and somebody wins, and that would be another coin flip. And finally, the winner of those first 2 games, if you will, play with 1 more coin flip. So you can do that with 3 coin flips. And that's a very natural, normal way to come up with a solution to this problem. However, I'm going to be very dramatic here. We can use the power of binary, and we can actually encode A, B, C, and D, each of those 4 different things, by using 2 bits. And so if we encode A as 0, 0, and B as 0, 1, and so on, we can actually determine who wins with only 2 coin flips. And I will freely admit that we spent far more time talking about this than it would have taken to do a 3rd coin flip, but that's kind of how my family works. But the next question is, how many bits do we need to represent a certain number of unique things? This was a really interesting conversation because it was how we go about encoding stuff in the computer. But if we're going to encode stuff, how many bits do we need to encode stuff? So let's say we have 1 bit. We can encode 2 unique values. We can have 0 or we can have 1. So 2 unique values. What if we have 2 bits? Well, that was the example we just did. We can encode 4 different things. And if we have 3 bits, we have 8 different possible encodings. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. And let me fix my glasses. I was counting up in binary, but those are the 8 different combinations we can get with 3 bits. Now, some of you may have already realized that if we have 1 bit, we can represent 2 things, and 2 to the power of 1 is 2. If we have 2 bits, we can represent 4 things, and 2 to the power of 2 is 4. And if we have 3 bits, we can represent 8 things, and 2 to the power of 3 is 8. So now I'll show you a slide with the biggest font you'll see throughout the course. The relationship is 2 to the b equal n. So if we know how many bits we have, we just raise 2 to the power of b, and that tells us how many unique combinations of those bits we get which tells us how many unique things we can represent. If you know how many things you want to represent, you can use the inverse relationship, right? We can take the log base 2 of n to calculate b, but I'll tell you, I personally never do that, right? I sort of go through the process, well, I'm trying to represent 12 things. How do I figure that out? Is 3 bits enough? No, 2 to the third is 8. Is 4 bits enough? Sure, 2 to the fourth is 16. We can never use partial bits. You can't say, oh, I need 3.7 bits. It's not how it works. You only get whole bits. But I don't usually use the log base 2n equation. I usually use 2 to the b equal n and work my way into however many bits I need. So that's it for this lecture. The two powerful ideas are we can encode anything with zeros and ones in a computer, and we have to because computers use binary, and we have this relationship, this 2 to the b equal n, that will tell us how many bits do we need to encode n unique things.